Alright, section 2.8 talks about inverse functions and one-to-one functions. One-to-one function is a function where if no two elements of its domain have the same image, meaning that whenever x1 is different than x2, then f of x1 is different than f of x2. Another way of checking to see if something is one-to-one is the horizontal line test. If and only if no horizontal line intersects its graph more than once, you draw a horizontal line, and if you only hit it once, it is one-to-one. Now, for an inverse of a function, it must first be one-to-one, and the inverse function f inverse, or f to the negative 1, like f with the little negative 1 there, has a domain b and a range a. For the original function, domain a and range b. Notice they're reverses of each other. The domain of one function is the range of the other. The range of one function is the domain of the other. They're inverses. They cancel each other out. So f inverse of y equals x is the same thing as f of x equals y. Okay, so if you got some function x and it maps f to some value y, or you got some y and you got the f inverse and it maps you back to x. Or in other words, if f takes you from x to y, then f inverse takes y back to x. Like I said, the domain of f inverse is the range of f, and the range of f inverse is the domain of f. They're opposites of each other. Example 1, is f equal x cubed 1-to-1? Well, you can graph it, and we know what the graph of x cubed looks like. It looks like this. And you can draw a horizontal line, and you only hit it once. Now another way you can do it is you can say if x1 is different than x2, then f of x1 has to be different than f of x2. Therefore, it is 1-to-1. Is g of x equal x squared 1-to-1? Well, if you graph it, it fails the horizontal line test. But you can also say for any two x values, they should not give you the same y value. Well, g of 1 is 1, g of minus 1 is 1 when you plug it into the function. So two different x values give you the same y value. That fails to be 1-to-1. Example 3, show that f of x equals 3x plus 4 is 1-to-1. Well, you can graph it. 3x plus 4 looks something like this, and all lines, unless they're horizontal lines, are 1-to-1 because they pass the horizontal line test. But you can also say, suppose x1 and x2 are such that their y values are the same. Well, that means 3x1 plus 4 equals 3x2 plus 4, and when you solve it, you end up showing that x1 equals x2. So the only time that the y values are the same is if the x values are the same. Okay, meaning the only time you'll get the same image or y coordinates if the x coordinates are exactly the same value. Therefore, it's 1-to-1. Now, here's how f and f inverse look. If you plug a 1 in for f, you get 5. Plug a 3 in for f, and you get 7. Plug a 8 in for f, and you get minus 10. Here, if you plug a 5 into the inverse, you get 1. 7 into the inverse, you get 3. Negative 10 into the inverse, and you get 8. The exact opposite. Notice they cancel each other out. Number 5, if you're given some function here with these individual points, f inverse of 3 has to be 4. F inverse of 5 has to be 7. So remember, this is your y coordinate and that's your x. Now, one other thing is that f and f inverse cancel each other out. So if you do f composite f inverse, you'll just get x. And if you do f inverse composite f, you'll just get x. Now they say show that f and g are inverses of each other. Well, find f of g and find g of f, and you should get x. Well, f of g, we know g is x to the 1/3. Now f says whatever you got, you cube it. So take this guy and cube it. Well, x to the 1/3 to the 3rd is just x. And what about g of f? Well, we know f is x cubed. And what does g say? You take the 1/3 power. So x to the third to the 1/3, that's just x. So now you've just shown that they are inverses. Now how do you find the inverse of a one-to-one function? First you write y equals f of x. You solve it for x. And you interchange your x's with your y's, and the result is your function y equals f inverse. Okay, so example 7, find the inverse of 3x minus 2. So you say y equals 3x minus 2. Okay, and then you add 2, divide by 3, and now you've got x equals everything else. So instead of x equals everything else, you say y equals everything else. So y, swap your y's with your x's. So 1/3 x plus 2/3 equals y. Here you go. Take f equals this guy and write y equals that. Solve it for x by multiplying by 2, subtracting 3, taking the 5th root. Now you've got x equals this, and you switch your x's with your y's, and now y equals the 5th root of 2x plus 3. There's your inverse. Number 9, y equals this guy. You set y equal to this guy, and you multiply both sides by x minus 1, and you get this. Now you bring everything that has an x to the left, everything that doesn't have an x to the other side. So minus y becomes positive y. 2x becomes minus 2x. Factor out an x. Then finally divide by y minus 2. Now you've got x equals everything else. Switch your x's with your y's, and there's your function. Example 10, you can graphically find your inverse if you graph the original function here, square root of x minus 2, and you take the points that you have and you flip them. 2, 0 becomes 0, 2. 3, 1 becomes 1, 3. 6, 2 becomes 2, 6. And when you graph that, that's your inverse. One of the things you can say about it is it is reflexive about the line y equals x. If you graph y equals x and you reflect it on that line, you will get the inverse. Now we can also find it the way we've been doing. So set it equal to y, square both sides, add 2, and now you got x equals that. So instead of y squared plus 2, it's x squared plus 2. And that's what that looks like again, but with a restriction for 0 to infinity for your domain. So, question number 1 says, a function f is one-to-one if different inputs produce different outputs. You can tell from the graph that a function is one-to-one by using the horizontal line test. Number 2, for a function to have an inverse, it must be one-to-one. Which of the following functions has an inverse? X cubed has an inverse. They ask you x squared, and you say no, x squared does not have an inverse. What is the inverse of the one you chose in part A? Well, the inverse of x cubed is cube root, or x to the 1/3. Number 3, the function f has the following description: multiply by 3, add 5, and take the third power. Write the verbal description for the inverse, and you do it backwards. Instead of third power, you take the third root. Instead of adding 5, you subtract 5. Instead of multiplying by 3, you divide by 3. And so you end up getting you write a verbal description for that, and then you find the algebraic expression for f and g. Question 4 says you got a graph here, and it says, does f have an inverse? And you say yes. And they say, if so, find f inverse of 1. Well, here's 1, and so x equals 4. Okay, and find f inverse of 3. 1, 2, 3 over here, and you get 5. Again, the input in your function is the y coordinate, and you want to find the x coordinate. Number 5, if the point 3, 4 is on your function f, then 4, 3 is in your function inverse. 6a, if f has an inverse, then f inverse is always the same as 1 over f. That's false. b, if f has an inverse, then f inverse of f equals x. That's true. Find out if these graphs are 1 to 1. This curve here fails the horizontal line test? No. Number 8 passes the horizontal line test? Yes. Number 11 fails the horizontal line test? No. Number 12 passes the horizontal line test. It is 1 to 1. 19, it says determine if the function is 1 to 1. Well, if you graph 19, you'll see that it's basically a parabola. Goes up faster because it's to the 4th power, and it fails the horizontal line test. 20, if you limit it from 0 to 2, it will pass the horizontal line test. So 20 is yes, it is 1 to 1. 23 looks like this. It fails the horizontal line test. 26a says if f of negative 3 equals 6, then f of f inverse of 6 equals negative 3. If f inverse of 12 equals 8, then f of 8 equals 12. 27. If f equals 5 minus 2x, find f inverse of 3. Well, remember, that's your y coordinate, so 3 equals 5 minus 2x. When you solve it, you get x equals 1. So f inverse of 3 equals 1. 31 gives you a table of values, and it says find f inverse of 5. And remember that the y coordinate is 5. You'll see from the table that the x coordinate is 4, since you have the point on the table of 4, 5. 40 says show that these are inverses of each other, 4x minus 7 and x plus 7 over 4. So we're going to find f of g, we're going to find g of f, and it should equal x. So f of g, we know g is x plus 7 over 4. And what's f say? 4 times it minus 7. So 4 times it minus 7. Well, 4 times whatever 4 is just x plus 7. Subtracting 7, they cancel out, and it just gives you x. G of f of x. F is 4x minus 7. And what's g? Says it plus 7 over 4. Here's your it. It plus 7 over 4. 7 minus 7, they go away. You just get 4x over 4, which is just x. F, 47f is this fraction, g is that fraction. So what's f circled g? We know g is this guy. Put it there. F says whatever you got, add 2, divided by whatever you got, subtract 2. So take this guy and add 2, same guy and subtract 2. Fastest way to clear out your fractions is to multiply by a common denominator of x minus 1. So x minus 1 times that just gives you 2x plus 2. 2 times x minus 1 gives you 2 times x minus 1. X minus 1 times this just gives you the 2x plus 2. And minus 2 times x minus 1 is minus 2 times x minus 1. Multiply everything out, combine, you just get 4x over 4, which is just x. And you do the same thing here with the second one, g of f. F is x plus 2 over x minus 2. And g says 2 times it plus 2 over it minus 1. 2 times it plus 2 over it minus 1. Multiply by x minus 2, cancels like before. Simplify and you get 4x over 4, which is just x. And so there's your proof of showing that f and g are inverses of each other.